Welcome back to TAE Certification Training Series. Let's continue with our external TAS metrics. Let's start today's session with metric number 8, number of pass and fail results. This is a common metric and tracks how many automated tests passed and how many failed to achieve the expected result. It's a standard way to measure how well your tests are doing and identify areas that might need attention or improvement. Then the next point is failures have to be analyzed to determine if the failure was due to a defect in the SUT or was due to external issues such as a problem with the environment or with the TAS itself. Okay, so now when a test fails, it's not just a dead end. You need to act like a detective. You need to figure out if the failure happened because of a bug in the SUT or if it was due to something external like issues with the testing environment or even problems with the TAS itself. So it's not just about counting passes and fails, it's about diving into the fails to see why they happened and what needs fixing. This helps you improve the reliability of your test and the quality of your software. Moving on to metric number 9, number of false fail and false pass results. False alarms analysis. Test failures analysis is time consuming. So when a test fails, it takes quite a bit of time to figure out that what went wrong. You have to really dive into the details, check logs, and really investigate the issue. And it's not a quick process. Frustration arises when test failures turn out to be false alarms. Imagine the frustration when you put in all that effort to figure out why a test failed, only to discover that there was nothing wrong in the first place. It's like a false alarm in a fire drill. False alarms occur when the problem is in the TAS or test case, not in the SUT. Now, false alarms happen when the issue is not with the software you are testing. Instead, the problem might be in your testing tools or the way you have set up the test case. It's crucial to minimize false alarms to avoid wasted effort. Minimizing false alarms is super important. You don't want to spend a lot of time and resources chasing problems that are not even there. It's like making sure that your smoke detector is not always going off for no reason. It saves time and resources for real issues. Then we have impact of false fails. False fails can diminish confidence in the TAS. Think of the TAS as your testing toolkit. When false fail occurs, meaning test failures are reported that are not real issues, it can shake the trust and confidence in your testing tools. This can make your testing team question the reliability of the automation, which is not a good thing because you do want them to have faith in the results. So it's important to keep false fails to a minimum to maintain confidence in your testing process. Continuing with metric number 9, we just had a look at false fail in the earlier slide, and now we'll have a look at the risk of false pass results. False pass results may be more dangerous. False pass results are a different kind of beast. So in this scenario, let's say that there was a failure in the SUT, but your automated testing didn't catch it. It's like a faulty security system that fails to detect a break-in. Next point is, in a false pass scenario, there was a failure in the SUT, but it was not detected by the automation leading to a pass result. So when a false pass occurs, there is a risk that you might miss a real defect in your software. It could be because the way you checked the result was not thorough enough or you used the wrong criteria. It's a potential problem hiding in plain sight. A potential defect might escape detection in such cases. It means that your automated test wrongly gives a passing grade even though there is an actual problem in the software it's testing. The issue slips through undetected, which can be a significant problem for software quality and reliability. So why do false pass results happen? Let's have a look. This can happen due to improper outcome verification, the use of an invalid test oracle, or incorrect expectations in the test case. So in order to understand it better, let's have a look at an example. Consider you are testing an e-commerce website. Your test case is supposed to confirm that users cannot make a purchase if they don't have enough funds in their account. The expected outcome is that the system should prevent users from making the purchase and should show an error message. Okay, now let's see that in this scenario where the false pass results can sneak in. Okay, so in our bullet point, the first reason was improper outcome verification. So if your test case only checks that let's say the purchase button is disabled when the user has insufficient funds but does not verify that the error message is displayed, then you might have a false pass. This is because the system might still allow the user to make the purchase through other means, for example, by entering a coupon code or using a different payment method without showing the error message. Therefore, your test case would pass even though the system has a bug. Next one is the use of an invalid test oracle. Okay, so now first let's see what is a test oracle. The test oracle is like the reference point that tells you that what the correct outcome should be. If your test oracle is wrong or does not reflect the actual expected behavior, it's like using a faulty map to navigate. Imagine that you assume that a website should allow users to make a purchase even if they do not have sufficient funds. However, the actual requirement is the website should prevent such purchases and display an error message. If you write your test cases based on your incorrect belief, your test will pass because they align with your belief. So, but your belief or assumption is not in line with the correct expectation for the software. So the test passing in this scenario are based on an invalid reference. So the point being made is that a valid test oracle should accurately reflect the actual requirements and expected behavior of the system. If your test oracle is based on incorrect beliefs or assumptions, it can lead to false pass results. I hope this is clear. Then the next one is incorrect expectations in the test case. Sometimes test cases themselves are faulty. If your test case specifies the wrong expected outcome, it is like following the wrong recipe while cooking. Let's say you expect the purchase to go through even with insufficient funds, but the actual requirement is to show an error message. If you run the test with your incorrect expectation, it will pass, but it does not reflect the true intent of the testing process. So false pass results can lead to a dangerous situation where a real problem in the software is not caught because the testing process is not properly aligned with the actual requirements or expectations. Okay, let's see now what are the causes of all these false alarms. False alarms can result from defects in the test code. See metric automation code defect density. Okay, just like how a small glitch in a machine can make it act up, defects in your test code can also cause false alarms. So we have a metric for this, which is known as automation code defect density, and we will shortly cover this. They may also be caused by an unstable SUT behaving unpredictably, such as timing out. Sometimes the SUT can be like a wild card behaving unpredictably. It might time out, go slow, or act inconsistently, leading to false alarms. The last one is test hooks can contribute to false alarms due to their level of intrusion. So test hooks are like extra sensors you add for better monitoring, but sometimes they can be a little too sensitive and they can trigger false alarms. So in conclusion, minimizing alarms is crucial as they can waste time and resources. False fails may hit confidence in the testing process, while false pass results are even riskier as they might overlook hidden defects, emphasizing the need for thorough verification and stable software behavior. Metric number 10, code coverage, which is our last external TAS metric. Knowing the SUT code coverage provided by different test cases can reveal useful information. So understanding how much your tests touch your software's code is quite informative. It helps you identify gaps and areas that might need more testing attention. This can also be measured at a high level, for example, the code coverage of the regression test suite. You can look at code coverage not just for individual tests, but also for the entire set of tests, like your regression suite. And it gives you an overview of how well your tests collectively explore the code. There is no absolute percentage indicating adequate coverage, and 100% code coverage is unattainable in anything other than the simplest of software applications. Okay, so there is no magic number for perfect code coverage, and achieving 100% coverage is nearly impossible in complex software. It's all about finding the right balance between thorough testing and practicality. However, it's widely accepted that higher coverage reduces overall risk in software deployment. When there is no perfect percentage, it's generally agreed that the more code you cover with tests, the safer your software deployment becomes. Higher coverage means fewer untested areas where bugs might hide. This metric can also indicate activity in the SUT. For example, if the code coverage drops, this most likely means that the functionality has been added to the SUT, but no corresponding test case has been added to the automated test suite. So changes in the code coverage can be like a signal from your software. If it drops, it's a hint that new functionality has been added to the software, but there are no tests in place to check it. It's a reminder to keep your testing in sync with software changes. We have now finished our external TAS metrics, and in our next session, we will cover the internal TAS metrics. Until then, happy testing.